In mathematics, when we want to describe relationships between two different sets, we normally use relations and more particularly functions as a tool. Vector spaces in linear algebra are not exceptions. In linear algebra, we use linear transformations to define relationships between vector spaces. Here is a formal definition for a linear transformation between two vector spaces. Here we have two vector spaces, V and W. Both of these vector spaces have a field of scalars F. When we say a linear transformation from V to W, we simply mean any function or any mapping L from V to W satisfying the following axioms. For every U and V in capital V, meaning to say U and V are vectors from the domain, and alpha in F, meaning alpha is a scalar, the following equations must hold. Number 1, the image of the sum U plus V under L must equal the sum of the images of U under L and V under L. Number 2, the image of the scalar multiple alpha times U must equal alpha times the image of U under L. Take note that in the first equation, we are using two additions. The first one being the addition that is in V, because it combines two elements from V, U and little v. On the other hand, the addition on the right hand side denotes the addition on the vector space W, as it adds two elements from W. On the other hand, in the second equation, the scalar multiplication here happens inside V. The scalar multiplication on the right hand side happens in W. If these two equations hold, we say that the function L is a linear transformation from V to W. You can think of a linear transformation as a mapping from the vector space V, so if this denotes the vector space V, to the vector space W. You can think of the linear transformation L as one that transforms each element V, little v of capital V, to an element to a unique element in W, namely L of U. This is why I sometimes call the space V, or the domain of the transformation, as the departure space. You can think of this as two airports connected by the plane L. So sometimes we call V the departure space, while W as the arrival space. L being a plane that transports people from V to W. Consequently, if L is a linear transformation from V to W, and if you take vectors V1, V2, up to Vn from capital V, and you take scalars alpha 1, alpha 2, to alpha n, then the image of this linear combination would be the linear combination of these images. This can be proven by simply beginning on the left hand side and then repeatedly applying equations L1 and L2 to each of the terms. And then whenever you get a scalar, you put them outside the function L, just like in property L2. Geometrically speaking, these linear transformations can be interpreted as follows. Linear transformations are functions or are mappings between two vector spaces that preserves 1. Coplanarity of vectors. Number 2. Collinearity of vectors. Coplanarity of vectors is preserved because whenever you get two vectors u and v from the domain v, they have the sum u plus v inside v. Of course, this vector u will be transported to w using L, and its image will be L of u, this vector. This v as well will have an image L of v in w, and on the other hand, and also the sum u plus v will have an image L of u plus v that will lie in w. So for the coplanarity to be preserved, it must follow that the sum or the image of the sum must be the sum of the images. That is what equation 1 is telling us. The image of the sum must be equal to the sum of the images. For collinearity, you can think of a vector. You can look at a vector u in the domain v, like so, and think of a scalar alpha u. By multiplying a scalar alpha to u, you can think of it as a stretching or applying a dilation on the vector u, like in the figure. Because L is a linear transformation from v to w, it will take u to w to a vector called L of u. Also, the product alpha times u will be transported to w using L, and its image will be L of alpha u. For L to be a linear transformation, the vector L times alpha u must equal alpha times L of u. Meaning to say, the image remained as a multiple of the image of the original vector. In the case when the domain or the departure space equals the arrival space, we call the linear transformation L from v to v, in this case, as a linear operator on v. To give you some examples, so here we got two vector spaces v and w over f. Consider the mapping zeta. Zeta takes v to w in the following manner. It takes every vector v from capital V to the zero vector in w. For you to have an illustration in your mind, you can think of this as the vector space v and this as the vector space w. Of course, w is a vector space. It must have a zero vector in it. So the zero transformation zeta simply sends the entire w to the single point 0w in the space w. So you can think of the zeta as a mapping that collapses v into a single point. So this is the zeta function. Now we can prove that this function in particular is going to be a linear transformation. To verify, let's take two vectors u and v from v. Then as you can see, if I take the image of the sum u and u plus v under zeta, it's going to be 0w, as it is the definition of zeta. It takes everything to 0. On the other hand, zeta of u plus zeta of v is going to be 0w plus 0w, which equals 0w, of course. Therefore, we can say that zeta of u plus v equals zeta of u plus zeta of v, which is the equation L1. To finish the proof, we need to prove that equation L2 also holds. This time, let u, we take a vector u from V, and we take a scalar alpha from F. We now look at the image of alpha times u under zeta, but this is just going to be 0 times W. And on the other hand, if we multiply alpha times zeta of u, you get alpha times 0 W, or properties of vector space, this tells us that this is just 0 W. Therefore, zeta of alpha u equals alpha times zeta of u, proving equation L2. Therefore, this mapping zeta is really a linear transformation called as the zero transformation. Another trivial example would be the following. If you take any vector space V over F, you consider the mapping denoted by IDV. The map ID takes V to V in the following manner. It simply takes in little v, and then it brings out, or it spits out little v as an image as well. So you can think of it as a trivial action because it does nothing on v. Whatever your input is, it's going to be the same output. This mapping is also a linear transformation and therefore a linear operator on V, because we have the same departure space and arrival space. This linear operator has a name. We call this the identity operator. You can check as an exercise that the identity operator is really a linear operator on V by proving that equations L1 and L2 are satisfied. We now look at a non-trivial example. Let's consider the function L from R3 to R2 defined by the following equation. So this function takes the point with coordinates x, y, z to the point in R2 whose coordinates are x minus y, comma, x plus z. As a matter of example, if let's say you have the input 1, 2, 3, the image of the point 1, 2, 3 is going to be this being your x, this being your y, this being your z. The image would be x minus y, comma, x plus z. So in this case, x minus y is going to be 1 minus 2. X plus z, on the other hand, is going to be 1 plus 3, and therefore this is negative 1, comma, 4. So this function takes the point 1, 2, 3 from R3, and it gives us an output which belongs to R2, namely the point with coordinates negative 1, 4. Now we now check that L is a linear transformation. To do this, we have to show that the two equations or the two axioms defining a linear transformation hold, namely equations L1 and L2. So for L1, we will be needing two vectors from R3. So let U be, let's say, x1, y1, z1, and V be x2, y2, comma, z2, be vectors from R3 because they are taken from the domain. So they look like that. Okay, they are representative points from R3. Then we look at L of U plus V. In this case, U plus V is going to be x1 plus x2, comma, y1 plus y2, comma, z1 plus z2. This is the definition of vector addition inside R3. Now, by looking at the definition of L, if you think of this as the x, this as the y, and this as the z, the image of this point under L is going to be the ordered pair x minus y, comma, x plus z. Following this formula, it will give us x1 plus x2 minus y1 plus y2, comma, x1 plus x2 plus c1, let me erase this one, c1 plus z2. If I simplify this expression, as you can see, this will become x1 plus x2 minus y1 minus y2, comma, x1 plus x2 plus z1 plus z2. On the other hand, if we look at L of u plus L of v, we will be having L of x1, y1, z1 plus L of x2, y2, z2. Right? By the definition of L, this is x1 minus y1, comma, x1 plus z1 plus x2 minus y2, so applying L on this, comma, x2 plus z2. Now, when you think of this as vectors from R2, this addition meant component-wise addition. Therefore, this simplifies to x1 minus y1 plus x2 minus y2, comma, x1 plus z1. So I'm looking at this and then going to add that, plus x2 plus z2. Notice that if we compare these two ordered pairs in R2, because the components are real numbers, the xi's and the yi's and the zi's are real numbers, addition is commutative. As you can see, this expression is equal to this expression. Similarly, this expression is equal to this expression. Therefore, we can confirm that the image of the sum u plus v under L is equal to the sum of the images of u and v under L. That proves that equation L1 holds. For the second part, we have to show that equation L2 also holds by picking an arbitrary u from R3 and an arbitrary scalar alpha from R. Now here, we're going to compare the image of alpha times u. In this case, alpha times u means a scalar multiplication in R3. We know that scalar multiplication in R3 is done in this way. We just multiply alpha to each of the components. So you get alpha x, comma, alpha y, comma, alpha z. By the definition of L, this alpha x, alpha y, alpha z vector will transform into the vector in R2. R2 equals alpha x minus alpha y, comma, alpha x plus alpha z. Again, when you think of this as the x, the y, and the z, this is going to be the x minus y, and this is going to be the x plus z. Right? On the other hand, when you look at alpha times L of u, this is going to be alpha times L of x, y, z. By the definition of L, this is going to be the ordered pair x minus y, comma, x plus z. Now, this multiplication is now happening in R2. Alpha times a vector in R2 means you are multiplying alpha to each of the components of the vector. So you get alpha times x minus y, comma, alpha times x plus z, which simplifies to alpha x minus alpha y, comma, alpha x plus alpha z. Notice that when you compare these two things, they are actually equal. Therefore, we can say that the image of alpha u under L equals alpha times the image of u under L. And therefore, we can now conclude that L is a linear transformation from R3 to R2. Alright, let's consider more examples. So let this symbol denote the vector space consisting of all functions which are continuous on the closed interval AB. So these are real valued functions whose domain is the closed interval AB, and these functions are continuous. For each continuous function f in this space, let us define I of f to be the Riemann integral, or the integral of f of x dx from a to b. We know from calculus that this definite integral, when evaluated, gives us a real number. We are going to show that the function I that transforms f into this integral, which is a real number, is a linear transformation from the space CAB containing the continuous functions f to the real number line R containing the real numbers. In order to do this, so for the L1 function, for the L1 equation, we take two functions f and g from the space CAB. Then, as you can see, I of f plus g, I being the mapping, means the integral from a to b of f plus g of x dx. But by definition of function addition, this equals f of x plus g of x. We know from calculus that this integral has the following property. The integral of the sum of two functions is the sum of the integrals. And therefore, as you can see, this transforms to I of f plus I of g, proving that I satisfies equation L1. For equation L2, we only need one function f from the space and one scalar alpha from R. Here we are looking at the image of alpha f under I. But this means, by definition of I, it's the integral of alpha f of x dx. But by the definition of this scalar multiplication, this is alpha times f of x. Again, from calculus, we know that this is equal to alpha times the integral from a to b of f of x dx. Therefore, this equals alpha times I of f. Therefore, I is a linear transformation from CAB to R. Later on, linear transformation from a vector space towards its field of scalars will be called linear functionals, when the arrival space is equal to the field of scalars. The linear transformation is called a linear functional. So the definite integral that you have learned in calculus is an example of a linear functional. Let us now consider another vector space. In this case, we look at the vector space R3 square bracket x. Again, R3 square bracket x contains polynomials. The polynomials of degree at most 3. So basically, the elements are of the form a plus bx plus cx squared plus dx cubed, where a, b, c, d are real numbers. Okay? So let's define d of f, where f is in R3 square bracket x, as f prime. F prime here means the derivative of the polynomial f. It is similar to the derivative that you have learned in calculus. So, in our case, the derivative of a plus bx plus cx squared plus dx cubed is exactly b plus 2 times cx plus 3 dx squared. Okay? As you can see, the result by applying d on a polynomial in R3 is now a polynomial in R2 square bracket x. We are going to show that d is actually a linear transformation from R3 square bracket x to R2 square bracket x. The reason is because of the following facts from calculus. If I get two polynomials p1 and p2 from R3 square bracket x and apply d on the sum p1 plus p2, you're simply taking the derivative of the sum. But we have learned from calculus that the derivative of the sum is the sum of the derivatives. So therefore, this is equal to the derivative of p1 plus the derivative of p2. For L2, if you take any polynomial in R3 square bracket x and a scalar alpha, if you evaluate d of alpha p, you get the derivative of alpha times p as shown. But remember, if you have a scalar before the derivative operator, the scalar simply takes out of the derivative operator, and what you have is alpha times the derivative of p from calculus once again. Therefore, this is equal to alpha times d of p. Therefore, we have confirmed that d is a linear transformation from R3 square bracket x to R2 square bracket x. Oh, so we have one more example, I think. So here we are now changing a vector space. Here the vector space is the space of n by n real matrices. For each matrix A in the space M and R, so A is a square matrix, we define T of A as follows. So we are basically adding A to its transpose. We will prove that T is actually a linear operator on M and R. Again, a linear operator means a linear transformation from a space to itself. So to check the axioms, okay, so let's begin with axiom L1. We will take two matrices A1 and A2 from the vector space M and R. Okay, and then we apply T on the sum of A1 and A2. By definition of T, we're going to add the sum A1 plus A2 to the transpose of the same sum. Now, using the properties of transpose, you can write this as A1 transpose plus A2 transpose. Because matrix addition is commutative, I can somehow write it as follows. Plus, I can group these two terms together, and I can group these two terms together. What we have is simply T of A1 plus T of A2, right? For equation L2, we only need one matrix from the vector space M and R, and one scalar alpha from R. And here, if we apply T on alpha times A, you get alpha times A plus the transpose of alpha times A, just like in the definition of T. But the transpose of alpha times A, based on the properties of the matrix transpose, is just equal to alpha times the transpose of A. Now we can somehow apply the distributive property over here. You get alpha times the quantity A plus A transpose, and therefore this is alpha times T of A. This proves equation L2. So therefore we can say that T is a linear transformation, actually a linear operator on Mn R. Take note that if any of these equations does not hold, then the given function is not a linear transformation. So in the following theorem, we are describing some properties or invariants that a linear transformation actually enjoys. Here, L is a linear transformation from V to W. The following must hold. So not only that a linear transformation preserves addition and scalar multiplication in the spaces, or in other words, coplanarity and collinearity, linear transformations preserve several other things. Number one, it preserves zeros. The image of the zero in V must always equal the zero in W. So 0 must go to 0 under a linear transformation. Also, for any vector V in the domain, the image of its negative is equal to the negative of the image of V. Number 3, L goes through subtractions as well. Meaning to say, if you get the difference U minus V of vectors from V, then the image of the difference is equal to the difference of the images in the same order. And number 4, a linear transformation always preserves linear dependence. Meaning to say, if I have a linearly dependent set of vectors in the domain, let's say S containing V1 up to Vn, then if we collect their images under L, now this is now a subset of W, that particular subset S prime is going to also be linearly dependent in W. So we are going to prove this one by one. For number 1, let's look at L of 0V. Take note that 0V is the same as 0V plus 0V. Now because L is a linear transformation, you can write this as L of 0V plus L of 0V. From this equation, if you subtract L of 0V on both sides, nothing will be left on the left-hand side. What we are left with is only the 0 in W. Therefore, L of 0V equals the 0 in W. For number 2, take note that if you take any vector V from the vector space or from the domain of L, if I add the image of V and the image of its negative, because L is a linear transformation, I can rewrite this as L of the sum V plus minus V. But V plus minus V in capital V is just the 0 in V, which according to number 1 is equal to 0 of W. So these elements in W, these are elements in W, right? When added together, they give us the 0 in W. Therefore, they are negatives of each other. In particular, L of minus V is going to be the negative of L of V. Next, take note that the difference U minus V can just be written as the addition u plus the additive inverse of v. Because L is a linear transformation, you can rewrite that L as L of u plus L of minus v. But L of minus v by number 2 is equal to the negative of L of v. Adding these two vectors together, that is the definition of L of u minus L of v. Finally, L preserves linear dependence. So, if we assume that S containing v1 up to vn is linearly dependent in v, so we are going to prove that the images of this vector still is linearly independent, but in W. To do this, we use the linear dependence of S in V. By definition, we can get scalars a1 to an, not all of which are zeros, such that this linear combination can be made equal to 0. Take note, not all of the AIs are 0. Thus, when you look at the 0 vector of W, it is equal to the image of the 0 vector of V, right? And this 0V can be replaced by this linear combination. And because L is a linear transformation, it preserves linear combinations. That is, the image of the linear combination is the linear combination of the images. But as you can see over here, these are the images of these vectors precisely in W. And they have coefficients which are the same as the AIs. Since these AIs are not all zeros and the sum, or this linear combination, equals 0, that meant to say that the images L of V1 up to L of Vn forms a linearly dependent set. And that completes the proof. We now have a question. Suppose now that instead we have a set of vectors in V which is linearly independent. And here you get a linear transformation that transforms V to W linearly. So we take the images of each vectors and collect them in a set called S prime. The question now is S prime linearly independent as well? In other words, we're asking that in the theorem, linear dependence was preserved. Would it be the same for linear independence? What do you think? So you can pause this video and think about this for a while if you want to work on yourself. And if you want to know the answer, you can just continue playing this video. So basically the answer is no. We have a counterexample, in fact. Let's consider the map pi. This time pi does not represent the number pi. Okay? Pi is just a symbol, and it's a mapping from R3 to R3 that takes xyz, the point xyz, to the point xy, 0. So this transformation simply zero out the third coordinate of the point. So geometrically, you can think of this as a mapping that flattens the three-dimensional space R3 into the xy plane. Why? Because if this is the xy plane, this is the x-axis, this is the y-axis, and this is the z-axis, for example. Every point xyz would be taken down on the xy plane. So the image of xyz will be xy0. So you are just projecting everything down towards the xy plane. So you can somehow think of this, or you can compare this with a camera. You can think of pi as a camera, the one that you're using every day, using your phone, no? You have a three-dimensional object, and then you take a picture of it. It transforms the 3D object into a two-dimensional picture, like so, using this type of projection. So for example, if you have a sphere over here, its image under the transformation is going to be a circle in the xy plane. This is why this mapping is an example of what we call as a projection. You can check that this projection map is actually a linear operator on R3. This is not hard to check because the formula is quite simple. If we look at the points or the set of points containing 1, 1, 1 and negative 1, negative 1, 1, notice that this forms a linearly independent set. I know that this is linearly independent because the reason is because negative 1, negative 1, 1 cannot be found in the span of 1, 1, 1. In other words, it's not redundant or it's not dependent on the vector 1, 1, 1. The reason behind this is because the span of 1, 1, 1 contains elements of the form AAA. And minus 1, minus 1, comma 1 is not of the form AAA, where A is a real number. Therefore, this set forms a linearly independent set on R3. If we take the individual images of these vectors under pi, I'm sorry, I think I incorrectly used L. This should be pi. The pi will zero out the third coordinates as shown. We are left with the following. S prime. The collection of images S prime contains 1, 1, 0 and minus 1, minus 1, 0. But as you can see over here, this set is now linearly dependent. It is because this vector is now an exact multiple of the first vector. In fact, if you multiply this by negative 1, you will get this. Therefore, this is redundant. So the set is linearly dependent. So as you can see, unlike linearly independent sets, linear independent sets are not, or the independence among vectors are not normally preserved by a linear transformation. So I think we need a specific property of the linear transformation to be able to preserve linear independence. So we will see that later. This time, let's consider a linear transformation L from V to W, but this time, V is finite dimensional. Finite dimensional means it has a finite basis or a finite coordinate system as shown on the board. So here, V in particular is n-dimensional. It has basis vectors V1, V2 up to Vn. Take note that if we apply L on each of these basis vectors and we call their images as Wi, for example, if let's say you take the image of V sub 1, the resulting image, call that W sub 1. You take L of V2, you call the image as W sub 2, and so on. You are going to do that I from 1 to n. Suppose that these V sub i's are already determined. Now, if V is an arbitrary element from the vector space V, we know from the previous lesson that because B is a basis, you can actually write the V as a linear combination of the V sub i's, like so. In fact, the scalars ai's over here are uniquely determined because B is a basis. Right? If you look at this equation and apply L on both sides, we get L of V as L of this linear combination. And because L is a linear transformation, this translates to A1 times L of V1 plus A2 times L of V2 plus and so on, AN times L of Vn. Because L of V1 is W1, L of V2 is known, W2, L of Vn is known, you get Wn. As a consequence, we can now compute for the image of V under L for an arbitrary element of V. So in general, once we know the images of L, of the basis vectors under L, then according to this computation, we also know the images of any other vectors from the space. Because any other vector from the space is just a linear combination of these basis vectors, and that allowed us to know the image of it using the properties of the linear transformation. In other words, a linear transformation is completely determined by its action on a particular basis. To further explain this idea, let's have the following example. So let L be a linear operator on R2 so that it takes the vector 1, 0 to the vector 1, 1. Also, it takes the vector 0, 1 to the vector minus 1, 1. Find a formula for L of xy for each xy in the plane. So, here, we have two pieces of information. One, we know or we are given that the image of 1, 0 is 1, 1. Also, the image of 0, 1 is minus 1, 1. Take note that the set E consisting of 1, 0, 0, 1 is a basis for R2. In fact, this is the so-called standard basis for R2, right? Right. So here we're given that L of 1, 0 is 1, 1. And what? L of 0, 1 is minus 1, comma 1. So if we want to find the formula for L of xy for any x and y, x comma y in R2, we have to first express xy as a linear combination of these two basis vectors. But because this is standard basis, writing xy as a linear combination is very easy. In fact, xy is simply just x times 1, 0 plus y times 0, 1. Therefore, if I want to know L of xy, I can just write just write this as x times L of 1, 0 plus y times L of 0, 1. But because L of 1, 0 is 1, 1, and L of 0, 1 is just minus 1, 1, I can now simplify this into xx plus minus yy. And therefore, as a result, I get x minus y, comma, x plus y. So this gives us a formula for L of xy for any x and y. There is a good geometric interpretation of this result, and I want you to figure it out. So in the next few slides, I'm going to show you how an arbitrary m by n matrix can be thought as a linear transformation from an n-dimensional space to an m-dimensional space. First, recall that if you have an m by n matrix and x is an n by 1 column vector, so A is a matrix, x is an n by 1 vector that's written in a column form. We have an n-dimensional vector because it has n coordinates. Only it's written in the column form. If I multiply A times x, you see that I have an m by n matrix multiplied by an n by 1 matrix. As a result, you know that the product is an m by 1 matrix. Let's call that product as y. This time, y is an m by 1 column vector. So as you can see, by multiplying A, the effect of multiplying A on an n by 1 column X is that it transforms the column vector X, an n-dimensional vector X, to an m-dimensional vector Y. Thus, the mapping that sends X to the product AX defines a function from the space Fn to the space Fm. If you think of these spaces, or if you write the vectors in these spaces in column form, right? Because normally we write the elements of Fn normally as follows, like this, right? So if you just express the vectors in column form, like so, you can think of multiplication of an m by n matrix 8 from the left of a vector. Again, if we multiply a matrix A on the left of a column vector X from Fn, what you will get is an m by 1 vector, or an element of Fm. To make this more formal, so suppose that A has entries aij, it's of size m by n, the scalars are in F. Define the map T sub A from Fn, the input function, the input domain is Fn, and the output space is Fm, or the arrival space. We will define TA as follows. So it sends the n tuple x1 up to xn to the m tuple y1 up to ym in the following manner. So here is your n tuple. It gets multiplied on the left by an m by n matrix. What results is an m by 1 matrix, which can be thought as an element of Fm. In other words, when we view the elements of Fn and Fm as column matrices, TA simply maps a vector x in Fn to a vector y in Fm of the form A times x. Symbolically, we can write this relationship using the following equation. TA of the vector x from Fm, n, equals A times x. We claim that such a function is a linear transformation. This is not hard to do, because if you have two vectors u and v from Fn written in column form, TA of u plus v is equal to A multiplied on the left of the sum u plus v. But because we have distributive properties for matrices, you get AU plus AV, which is TA of u plus TA of v. At the same time, if you have the scalar multiple alpha times u, apply TA on it, we are actually multiplying A on the left. Property of matrix operations, you get alpha times A times u, which is alpha times TA of u. Therefore, TA is a linear transformation. This particular linear transformation that was produced using the matrix A is called a matrix transformation. To give you an example, let's consider the 2 by 3 matrix A with the following entries. So, this matrix A of size 2 by 3 will transform elements from R3 to R2. So, it's in the reverse order. Okay? So you can think of this matrix as a transformation from R3 to R2. So when you write a vector from R3 this way, okay, so TA of x means, and if you multiply A times x, you get 1, 3 minus 2, 5 minus 1 minus 3 times x1, x2, x3. If you do this, perform this multiplication, as you can see, what results is a 2 by 1 matrix. And the 2 by 1 matrix can be calculated as follows. You take rows by columns, then rows by columns. So for the first entry, we get x1 minus 2, x2 minus x3. The second entry will be 3x1 plus 5x2 minus 3x3. Therefore, upon multiplying a to the left of this vector, we have obtained the following vector. Therefore, an explicit formula for TA, when you write x in the following form, so we use x1, x2, and x3 pala, it is equal to the vector in R2 with the following formula. So you don't need to check. This will always be a linear transformation, or a function generated using this method will always be a linear transformation. Did you understand? So, if you think about the total number of matrices that we ever have, no? That's how big the number of examples that we can actually produce. Every matrix defines a linear transformation from Rn to Rm. Another example, so this is now geometric in nature. The matrix A here is a square matrix. So you can think of it as a linear operator because it's a square matrix. It transforms R2 to itself R2. So here, you're asked to sketch the square in R2 with the following vertices. So actually this square is the unit square. So if we try to sketch, okay, so let's say this is 1, 2, 3, 1, 2, 3, okay. So the square is going to be this square, okay. So this is O, this is A, this is B, this is C. Now, to sketch the image of this square under the transformation, we're going to get the image of its vertices. Because linear transformations preserves collinearity and coplanarity, it is enough to locate the image of these vertices. For example, what will be the image of O? The image of O under the transformation, so if we take that to be there, because O is the 0 vector, we know that that will also be the 0 vector. So the image of O is itself under the transformation. Now what would be the image of A? The image of the, oh my gosh, so we use the symbol A for the vertex and A as well. Oh my gosh, so let us just think of this A as an A different from this A, okay? So basically, we are looking at the image of 1, 0. Now, how do we calculate for the image of 1, 0? So, in Scratch, we're going to do matrix multiplication. So, we simply multiply 2, 1, 0, 1 to the column vector 1, 0. That's how we do the matrix transformation. As for the image is going to be, so, shortcut pala. So you just write the matrix A over here, and then you write the vertices over here, 0, 0, 1, 0, 0, 1, I'm sorry, 1, 1, and 0, 1. Kasi you're multiplying the matrix to the left of each of these vectors. And then we perform the multiplication. As you can see, you get here 0, 0, and then here you get what? You get 2, you get 0, 1, 1 will be transformed to 2 plus 1, 3, 0 plus 1 is 1, and then here you get 0 plus 1, 1, 0 plus 1, 1. Is that correct? Yeah, I hope so. Therefore, A prime, which is the image of A, is going to be, when you look at this, it's going to be 2, 0. Now the image of B is going to be the image of 1, 1. In this case, that's 3, 1. Therefore, the image of C, the image of 0, 1 is going to be 1, 1. So using the same Cartesian plane, you see that, let me color it like by blue. So the image of O is the same vertex O, but A prime, the image of A is going to be now on 2 zeros. This is now the image of A. The image of B is now at 3, 1. That's B prime. And the image of C is now at 1, 1. So this is now C prime. Because linear transformations preserves lines, OA is connected by this line segment over here. Therefore, in the image, the images of their vertices will still be connected by a line segment. So therefore, that line segment will be stretched by this factor. This line segment will be, the image will be somewhere there, the one connecting A prime and B prime. This line segment will have an image which is exactly equal to this, and the image of this line segment is going to be this line segment. So as you can see, the unit square becomes a parallelogram. In linear algebra, this is what, or in geometry, this is what we call as a shear transformation. Shear transformation. It's like, supposing you have a picture over here like that. Its image after the transformation will be sheared by a factor of 2, just like this one. Okay? That will be the image. Okay? And I guess this is the last example. So here, you're going to find the matrix of the transformation, which gives a rotation of R2 of the Cartesian plane, about the origin. So the center of the rotation is the origin, and the angle of rotation is 90 degrees. Also, find an explicit formula for such a transformation. So this time, we want to get a matrix for a transformation that is described in words as a rotation in R2 about the origin at an angle of 90 degrees. So if you want to think about this, you can pause this video. But if you want to know the answer right away, you can just continue playing the video. So here, we use the fact that the linear transformation is completely determined by its action on a basis. So here, we just use the standard basis. The standard basis for R2, in this case, is the basis containing the vectors 1, 0 and 0, 1. So I'm going to draw them in the Cartesian plane, like so. So this is the y-axis, this is the x-axis. So let's say 1, 1, 2, I'm sorry, 1. Alright. So 1, 0 is this vector. So let me use a thicker pen for 1, 0. And this is 0, 1. Alright. So if I rotate, let's say this is E1, okay? Let me E1, E2. So we would like to know to where would these basis vectors go if we apply a rotation about the origin at an angle of 90 degrees. So if I rotate the plane 90 degrees, counterclockwise of course, E1 will be moved somewhere else now, right? So the image of E1 is going to be, so let's use annotation, let's say rho B denote the rotation, okay, about 0, 0 at an angle theta, no, 90 degrees, right? Then to where would E1 go? E1 is 1, 0. If you rotate this 90 degrees at a particular angle, this will move somewhere here. So your E1 prime would be there. That's E1 prime, right? Alright, so that's E1 prime. Now the image of, so that's going to be 0, 1, right? Now the image of E2 is going to be, so this vector will now move 90 degrees over there, so the image is going to be this vector. We can now call this as E2 prime. So the image of 0, 1 is now at negative 1, 0. Right? So therefore, if I want to know the image of an arbitrary point, I just need what? I just need to write xy as a linear combination of 1, 0 and 0, 1, like so, in this case. Sorry, wrong, again. Xy is x times 1, 0 plus y times 0, 1. Now applying rho, x rho of 1, 0 plus y rho of 0, 1. But rho of 1, 0 is 0, 1 and rho of 0, 1 is what? Negative 1, 0. So if you simplify, we get minus y x. So this gives us a formula for the rotation. But the problem also asks for the matrix of the transformation. So how do you get the matrix? So here we are looking at, so the formula is this. This is rho minus y over x. So we're looking at a 2 by 2 matrix, which when multiplied to xy will give us minus y over x. The technique to generate this matrix is to look at the images that the images of the basis vectors under the transformation. So in this case, the first standard basis vector 1, 0 was sent to 0, 1. Now the standard basis vector 0, 1 was sent to minus 1, 0. So the technique is to place this in the first column and this on the second column. So that's going to be 0, 1. No? Rho of 1, 0 is 0, 1. Rho of 0, 1 is minus 1, 0. So if I place this in the first column, this in the second column, so this is what I will get. You can verify that this multiplication will actually work. So the matrix of the transformation is what? 0, minus 1, 1, 0. And the transformation that A induces is the rotation rho. Okay? So that's it for this lesson. We will continue next time and we will look at some more aspects of linear transformations. Alright, see you in the next video.